Okay, I'm gonna be talking now about distributed systems. Okay, what is a distributed systems? It's a set of computers that are connected together. Okay, so a set of machines that are connected together. We call that distributed system. So the definition here: collection of separate, possibly heterogeneous, systems networked together. What is heterogeneous? A set of items. It could be computers, it could be robots, it could be books, it could be whatever. They could be homogeneous or heterogeneous. Here, the word is written here, because there's no space. What is homogeneity and what is heterogeneity? When the systems are similar, they are called homogeneous. When they are different, they are called heterogeneous. So when you have a set of computers and those computers are all, let's say, Windows-based and the machine itself are similar, so same memory, same processor, and so on and so forth, we call them homogeneous, homogeneous set. Heterogeneity when you have few computers that are Windows, few others that are Mac, a third set that are Linux, we call those heterogeneous. So homogeneous or homogeneity and heterogeneity, it targets the how common the stuff is, or how similar they are. I don't want to leave this point because I want to talk about something here. In this book and in most of the prototyping and the operating systems book, they address homogeneity and heterogeneity based on the architecture, so the hardware architecture. And maybe the Windows, and so also the operating system, which is something I don't really agree with. So I'm gonna be telling you my point of view here, and it's up to you to follow what most of the references are adopting, or you can actually follow my point of view. It's up to you. Imagine that we have two robots, robot 1, robot 2. Robot 1 and robot 2. Robot 1 moves with the speed of 10 kilometers per hour. Robot 2 moves with the speed of 20 kilometers per hour. If there is a task for the robot to move stuff from location A to location B, with the speed of 5 kilometers per hour. Then the two robots here are literally homogeneous. Why? Because both of them can achieve the task. So you can literally pick any one of them and the task will be achieved. All right? If the required task, however, is to move this item with the speed of 15 kilometers per hour, okay, then they're no longer homogeneous. Now they're heterogeneous. Why? Because robot 2 can achieve the task, whereas robot 1 cannot. What does it mean? It means that the hardware and the installation of the operating system, it's not enough to judge whether machines are homogeneous or heterogeneous, right? Okay. Also the ability to achieve tasks is one of the parameters, right? You would tell me, but you know what? The computers, if when it comes to computers, if they have the same machine structure and if they have the same operating system, then they will be able to achieve the exact same task, which is right. But you need to remember that operating systems are not just for computers, right? You install the operating system on robots, you install the operating system on space shuttles, you install them on many other systems, right? So taking, in my point of view, and you are free to take it or not, taking the tasks, the ability to achieve tasks into consideration is a very important factor to determine whether the system is homogeneous or not. Okay, just wanted to comment on that. Let's go back to the distributed systems. Now, network, what is a network? It's a set of machines connected together, right? And by the way, the network doesn't have to be computers. The networks could be sensors, right? We have now sensor networks when it comes to the smart cities, and we do have what we call the SDNs. Is a communication path. So network is a communication path. What does it use to communicate? If you have many computers, let's say this is computer 1, computer 2, computer 3, okay, computer 4, and so on. What do they use to communicate? They use what we call a protocol. And for those who studied networks, they know what I'm talking about. Okay, the most famous protocol, it's not the only one, by the way, but the most common is the TCP Ip. What does it do? It allows the communication between computers. Okay. The good thing about having protocols is the fact that the heterogeneity is hidden. So the protocol actually handles the heterogeneity. So if you have a Mac and your friend has a Windows, you still can talk, you still can chat, you still can communicate using two different or two heterogeneous machines, okay? Now, the network can broadly be classified to be one of those four. Local area network. What is local area network? LAN, local area network. When you have a network that is, connecting devices at an office or even a company or something, we call it local area network. Okay. When we talk in size, I'll talk in size. So this is number one, the smallest. There is personal area network here. This is even smallest. I'll give it number 0, which is if you have two computers at home and the TV, and you can literally connect them all together with a PAN, a personal area network. Local area network is a little bit bigger. Okay, so you have a company wise when it comes to area. All right. The third one is Metropolitan. I'm not sure why the authors sorted the different networks this way, but anyhow. What is bigger than the local is the metropolitan, and the metropolitan area network is a network that binds a few buildings together. So we can say that our network at the AUM is metropolitan area because all the machines in business buildings, engineering buildings, and so on are connected together. So we can actually say this is metropolitan area network. Of course, I don't know the structure of our network at the AUM. This is just an example. It might be just set of local areas. They might not be bound together. The biggest one that is not really limited by area is the wide area network. Okay, the wide area network. And the wide area network is, it could be a whole country, it could even be a whole region or a continent. Okay, a wide area network. Okay, it's not really bound by space. Look at this network operating system. What is this? It's the original 7 layers if you studied networks. Okay, 7 layers from the physical network all the way, physical network, and then, all the way until the last layer that you have. Okay, which is the application layer. All right, they used to be 7, the TCP IP, now the new one, minimize it to 4, but, those are the operating system. When you go down, data are being, kind of processed this way until it goes down to the physical layer as bits, okay? And then this one, when you receive, it goes all the way up from the bits all the way until messages that you can understand. So this is the network operating system, and the whole network operating system is actually part of the operating systems, right? It's part of it. So this is the network operating systems. Okay, so it's part of it. This is a very, very important statement. Illusion of a single system. Here in Kuwait, you're chatting or communicating with someone in Australia, and another one in Canada, and another one in Norway. You feel that you all are in a single system. It might not be, right? It might not be. Space-wise and operating system-wise. So you could be talking to someone who has Windows and you have Mac or Linux or whatever, and you don't feel the difference. This is also an illusion of a single system. All right? Okay. Let's now talk about computer system architecture. Most systems use a single general purpose processor. Of course, I would have hoped that authors would remove this statement right from their book and slides, simply because it's no longer valid. There is no device now that has a single general purpose processor. Okay? Most systems have a special purpose processors as well. Okay, that's true. All right. Now, we have something called multiprocessors system. So one new word we have learned now is multiprocessing. Okay. We have seen before multi-programming. Please do not mix between the two of them. Many students use those two words like, as if they're the same word, which is not really the case. Okay? To talk about multi-programming and multiprocessing and the difference between them, I'll first talk about the concurrency and the parallelism. Okay, I know I talked about it before, but I have to remind you with it. You have concurrency, you have parallelism. What is the difference? Concurrency means that processes share time, over the whole process period. So as an example, you have here P1, P2, P3, and so on. You assign P1 will execute from time 0 to time 2, and then P2 will execute from time 2 to time 4, and so on. This is concurrency. Parallelism, it means that they all execute in the exact same time. As I mentioned before, most of the books, whether it's operating systems books or prototyping, they do distinguish between the two. They do present the two as two different things, which is not really the case according to me. That's how I see it. I see that concurrency is the general set, parallelism is a special case. So again, for those who study operating systems, object-oriented, the parallelism inherits from concurrency by increasing the number of queues. Okay, so every parallel is concurrent. Every parallel is concurrent. But not every concurrent is parallel. Okay, it's not the case, because concurrent could be a single queue which is not parallel. Okay, but you could have multiple queues, or in this case you have parallelism. So anyhow, that's the same difference between all multiprocessing and multiprogramming. The multiprogramming means that you load in memory multiple programs. That's multiprogramming. But it doesn't say anything about how you will execute those programs. You could execute them as batch, as we talked about before, or you could time share. Okay? Or you can execute them in parallel. How would you execute them in parallel if you have multiple processors? This is processor 1, this is processor 2. So in the same time, when you're executing P1, you could also be executing B2. So what is multiprocessing? Multiprocessing is executing processes in parallel. Why? Because you have more than one processor. What if you have a single processor? If you have a single processor, you can do multiprogramming by loading more than one program into memory. But the execution here is going to be either sequential as a batch or timeshare, but never parallel. Okay, so that's the difference between multiprocessing and multiprogramming. Please do not mix between them. Usually when we talk about multiprocessing, we talk about hardware architecture. Okay, multiprogramming is pure software. Okay, so when you have multiprocessors, those multiprocessors can be bound together with tightly coupled or loosely coupled. Okay, I said something wrong here, I'm sorry. I'm saying when you have more than one machine, okay, or processor, they could be related together with either tightly coupled or loosely coupled. In the case of the multiprocessors, usually it's tightly coupled, okay? You see here, also known as parallel systems. parallel system, the multiprocessors. That's why I told you, it's always parallelism is related to multiprocessors. Okay, and then tightly coupled systems. What does it mean to be tightly coupled? It means that the two processors have shared memory together. That's tightly coupled. And when the processors have shared memory this way, they can talk together through this memory. So PR1, processor 1 can write something, PR2 can read it from here. And then PR2 can respond and write something here, and PR1 can read it from here. See? Tightly coupled. What is the opposite of tightly coupled? Loosely coupled. Okay? How would it be loosely coupled? Every processor has its own memory. That's what we call loosely coupled. Okay, you should have studied that, I guess, in prototyping. Okay, and in the case of the loosely coupled, the communication between processors are now messaging. Why? Because they don't have shared memory. They message, okay, as you will see later in chapter 3. So I hope this is understood. What is multiprocessors, what is multiprocessing, what is the difference between multiprocessing and multiprogramming. They're not really related. Okay, the concurrency and parallelism, I made it clear the way I see it. It's up to you whether you follow what I said or go after the definition of the book. It's really up to you. Now, the advantages of the multiprocessing is increased, what is this word? Throughput. Very important word that we will use throughout this course, the throughput. What is the throughput? Throughput is how many processes you finish per time unit. Let's assume that you are reading a book. Okay, you're reading a book. So the time unit, I'm going to be choosing it as an hour, okay, per hour. So the number of pages you finish per hour is your reading throughput. So I could, finish, let's say, 10 pages per hour. So my throughput is 10. Now you can finish 15 pages per hour. So your throughput is 15. Usually we get the average throughput, right? So, it's usually the average, so that it's, more reliable reading. We have also economy of scale. So, increasing parallel systems, would be more economically. Okay, instead of buying two different computers and trying to connect them together and so on. Increased reliability. Why? Because of the fault tolerance. Fault tolerance is very important word, not for operating systems, but for engineering in general. What is fault tolerance? As an engineer, when you build a system, okay, you need to make sure that it can tolerate any fault that can happen. So as an example, okay, you have a program, you wrote a program that calculates X divided by Y. And Y is being read from the user. If the user enters 0 and your program breaks because you're dividing by 0, you don't have any fault tolerance here. How would your system be having a fault tolerance? You either use, try and catch, so exceptions, for those who studied exceptions, or you can just use an if statement, right? If Y doesn't equal 0, then get x divided by y, else go for an error message or whatever. Now you are kind of tolerating the fault. Tolerating the fault, of course, is much more than that. This is a very naive example. It's much more than that. You can also tolerate the fault even when you're getting into the error state. You should be able to tolerate it, okay? Here I'm preventing the error from the beginning with my if statement. But I guess you got the idea here, okay? So this is the increased reliability. Why would that be? Because you have two processors, right? You have two processors here, okay? Since you have, multiple processors. If you have multiple processors here, you can do, you have an increased reliability, because if one of them is down, the rest will, still do the job. So in multiprocessing, you have asymmetric and symmetric. Symmetric is homogeneous, and asymmetric is heterogeneous. Okay, so asymmetric means each processor is assigned a special task, a specific task. So you cannot really do any task for this processor. And I give you an example. And here, the symmetric, each processor performs all tasks. An example for asymmetric is what we talked about in the DMA. So here you have a general purpose processor, and here you have a very dedicated processor for dealing with I/O. This is very asymmetric, because this is not really a general purpose. It cannot do anything but reading and putting into memory, right? So here you go. Here is multiprocessing, but still it is, asymmetric. So you cannot take this processor and make it do calculations. All right. Now, the symmetric multiprocessing architecture, it looks like this. See, this is tightly coupled. How did I know? How did I know? Here, shared memory. Do you see? So here you have processor 0, which is CPU 0. It has its own registers and cache. Processor 1 has CPU 1, registers and cache, and both of them are dealing with the same memory. So processor 0 wants to talk to processor 1, it will write it here, and then processor 1 will read it from here, and vice versa. Okay, so this is symmetric multiprocessing architecture. We have a special kind of this symmetric multiprocessing architecture, which is the dual core that you all heard of. All our phones now are dual core, okay? All our laptops and most of the computers, if not all, and so on, they are dual core, okay? What is it? Multi-chip and multi-core. What does it mean? Look at this. Here you have one processor. See the difference here? How many processors did we have in the symmetric multiprocessing? Here, processor 0, processor 1, 2. Look here for the dual core, it's one processor. But how many CPUs does it have? 2. This CPU has its own registers and cache, and this CPU has its own register and cache. And we put another cache here, okay, to work as, a caching system between the main memory that is being shared between the two cores and, the L1 cache and L2 cache, which makes it much, much faster, dual core. Okay, so one processor with multiple cores. How about this? Look at that. Here you have a CPU with its own memory, a CPU with its own memory, a CPU with its own memory, and a CPU with its own memory. What does it make this system loosely coupled. There is no shared memory. So how do they connect? How do they interact? Messages. They message each other. Okay, so this is, the non-uniform. We're going to be talking about all those details in chapter 3. Like multiprocessor systems, okay, but systems working together, look at that. Usually, we share storage via storage area network. That's the clustered. Okay, we call it storage area network. Like what? Like the huge drivers, disk drives or whatever storage we have in our networks. I don't know if you guys have access to that, but we do have such thing. Okay, we call it the same. It provides high availability service, okay, for data and storage and so on. You have a symmetric cluster and symmetric cluster. We already know now what asymmetric and symmetric are. Okay. The asymmetric cluster has one machine in hot standby mode. Hot standby mode means it's waiting for something to happen. And this has multiple nodes running applications. Very, very different. Okay. Some clusters are, look at this, high performance computing. We have that in our labs, HPC. Okay. An application must be written to use parallelism. Let me show it to you. Here it is. Look at that. Here is the storage area network. You have here one computer. They can talk to each other, and all of them are accessing the exact same storage area. Those computers, as I've mentioned in the last slide, they don't have to be uniform. They don't have to be symmetric. They could be asymmetric. Okay, so those are the clustered systems. Here is how the PC motherboard looks like. Don't worry, this course as an operating system is not related to any hardware. It's basically a set of approaches and algorithms that are very easy to understand. I'm just saying that because many students, when they see this picture, they panic. So don't worry, this is just a picture that's not really related to what we're gonna be doing. As I mentioned in the beginning, we just see this kind of hardware and so on because we're gonna be dealing with the software that is controlling it. Okay.